Hello, in this video I will present a work on adversarial likelihood estimation with one-way flows. Generative models usually have to trade off between efficient sampling, high-quality images, and having an explicit probability density function. For example, generative adversarial networks, GANs in short, are able to efficiently generate high-quality images, but they can suffer from mode collapse and cannot estimate the probability of a sample. Normalizing flows can compute exact and explicit probabilities and are also able to generate images efficiently. However, the results are not as high quality as GANs, and their architecture is constrained due to their bijective requirements. Diffusion models can generate images with high quality and provide an explicit probability estimation. Yet, this probability estimation is only a lower bound of the true probability, and generation is slow because it performs hundreds of network evaluations. In this work, we propose an adversarial method that can generate high-quality images with efficient sampling and explicit probability estimation. We follow energy-based models and define a function d, chosen as a neural network with parameters theta, that returns the unnormalized log likelihood of an input image. This lets us define PD as the exponent of the output of d, divided by a normalizing factor marked as zeta. To compute the normalizing factor, we take inspiration from important sampling and introduce a new distribution, PG. This lets us write the normalization factor as the expectation of the ratio between PD and PG. We define PG to be the push-forward density of a neural network G with parameters psi. G receives random noise as input and outputs an image that is a sample of PG. I will explain more about G later. We train the density estimator by log likelihood maximization. After expanding, we see that the objective requires summing over samples from PG. If we set the number of samples to 1, we can see that this is exactly the objective of the Wasserstein GAN discriminator. This suggests a connection between energy-based models and GANs, and that Wasserstein GANs compute an implicit one-sample approximation of the normalizing factor. Following important sampling, the error of the normalization factor is minimized when PG matches PD. Hence, we define the objective of G as the minimization of the KL divergence between these two. The resulting objective has two terms, one that is the same generator objective from Wasserstein GAN and one that maximizes entropy. We hypothesize that the additional entropy term will help avoid mode collapse. Optimizing the density estimator objective and entropy requires access to the probabilities of the generated samples P of G of Z. While we could use normalizing flows, they constrain the possible architectures we can use in our models. However, note that in our case, we only need the probability of the generated samples and not of the true data samples as with normalizing flows. Without this bijection constraint, we have almost complete freedom in designing the generator. Here, we propose a method to estimate PG for almost any generator architecture, which we call one-way flow. Our method is based on the change of variables formula, which requires the computation of the inverse determinant of the Jacobian. The determinant requires the Jacobian to be square. We achieve that by concatenating independent and identically distributed random noise to the latent vector. To compute the Jacobian determinant efficiently, we use this equality from Sol-Dicksteins. This equality is based on uniform sampling from a hypersphere surface. We approximate this equality with a one-sample empirical mean using the Jacobian vector product. This lets us write the generator objective simply as written here. Let's see some results. We test our model on two mixtures of Gaussian distributions, a ring of 8 modes and a grid of 25 modes. The table compares the number of modes captured and high-quality rate between our generator and other models. The high-quality rate represents how many samples were close to a mode, and the number of modes captured is measured by how many of the modes are nearest to at least one high-quality sample. Our generator consistently captures all modes and produces the highest rate of high-quality points. Note that the GAN achieves a higher high-quality rate, but that is due to mode collapse. Our model also allows us to compute the density of each point using the discriminator, and we show in the figure to the right that the captured discriminator density also matches the modes of the true density. We tested our method on the Celeb A and CIFAR10 datasets, and found that our method attains better FID than a Wasserstein GAN with the same architecture. Here we can see images generated by our generator. We sorted them by the unnormalized log likelihood computed by D. We see how normal faces receive high scores while deformed faces get low scores. Finally, we show some qualitative results. First, we interpolate the latent space and draw the generated latents. The resulting images show that the interpolation works well, generating a face each step. Recall that to square the Jacobian, we concatenate random noise to the latent vector. In this experiment, we use a constant latent vector and randomize the noise for each generation. The images here show that the low-dimension latent is able to capture the identity and structure of the image, while the added noise changes small attributes such as colors and fine features. To conclude, we show that density estimation with GANs is possible and is connected to energy-based models and Wasserstein GANs. We also show that maximizing the entropy of the generator arises naturally from the formulation and can prevent mode collapse. To work with the probabilities of the generated samples, we introduce one-way flows, which allow an efficient computation of density during generation. Finally, we proposed an efficient generative model that generates high-quality samples with explicit probability. For more details, use the link or scan the QR code. Thank you for your attention.